Hey, this is Josh from LeetDev, where we try and explain programming questions as simple and concise as we can. Today, we'll be looking at the problem Two Sum as the first part of our four-part series of the sums. According to LeetCode, Two Sum is a very popular question asked a lot by Amazon, Facebook, Microsoft, and Google. If you want to start your LeetCode career off on the right foot, this is the problem to start with. Given an array of integers num and an integer target, the goal of this problem is to return the indices of the two numbers that add up to a target, and these numbers are guaranteed to exist in our array. Looking through our example, we have example 1. We were given 2, 7, 11, 15, and we want to find the target 9. As you can see, on index 0 and index 1, they add up to 9, so we return that as our answer. In example 2, we're given 3, 2, and 4, and our goal is to find the target 6. Clearly, the answer is index 1 plus index 2, which will give us 6. And then finally, in our third example, we want to find the target 6. If only two elements in the array, we don't really have much of a choice, and 3 plus 3 equals 6. The first way to try and solve this problem is by using a brute force solution where we try every pair of number with each other. To accomplish this, we use a double nested for loop where we have I and j. We just add these values together and see if they equal our target 9. So at index 0, we have 2, and at index 1, we have 7. 2 plus 7 equals 9, so that gives us our answer and we return them. However, walking through the algorithm, what we will see is we'll try index 0 plus index 1, index 0 plus index 2, index 0 plus index 3, and then once we finish our inner for loop, we increment our outer for loop to I equals 1. J would start over at index 2, and then we would add index 1 of index 2, index 1 and index 3, and so on and so forth. This algorithm will give us a O of n squared runtime because we had to try every single combination with each other. Space-wise, this would be O of 1 because we are not storing any additional data structure. So we got that going for this algorithm. Our brute force solution takes O of n squared. If we want to do better, we have to sacrifice some of our space to get a better runtime. We can do this by storing our values in our index in a hash map. To reiterate, a hash map is a data structure that takes in a key and value pair, where our key would be the number that we are currently looking at, and our value would be the index that it is located in. The benefits of a hash map is that it is a constant space operation to insert the key value pair into our map, and more importantly, is a constant time operation to look up to see if the key and value pair is inside our map. To solve this problem using the hash map, we accomplish this in 2 steps. First, we'll scan through everything in our array and put all of the numbers we've seen in our map. And then we would scan through the array one more time to see if we can find if the target minus our current array index value is in our map. For example, let's say we are at index 2. Our target is 26, and we subtract 11, and that will give us 15. If we can find 15 inside our map, that means that somewhere in here there is a pairing that would add up our current value that we're at, which is 11, and that would give us 26. By using this map, we can quickly find the index of where 15 is, which we can see is 3, and then we can quickly return 2 and 3. Now let me quickly clean this up. I've adjusted our problem a little bit. So notice that our target value is 6, and that our array is now 3, 2, and 4. One edge case that we didn't talk about is what happens if one of our number complemented with itself equals our target number. In this instance, 3 plus 3 equals 6. This would cause our algorithm to return the wrong value because it would return the answer 0, 0, while the answer is actually 2 plus 4. So what we have to do is whenever What we have to do is when we are scanning through our array again and checking for target minus our current value, we also have to ensure that the index that we find is not the same as our current index. So quickly walking through this problem. We start at index 0 and we add the key value pair 3 and its index 0 in our map. We advance our array. At index 2, we add the pair 2, 1, and we continue, and we add 4, 2, and then we add the last key value pair, which is 15, 3. Now, when we scan a second time, we'll find if target minus our current array value exists in our map. In this instance, we'll find that 6 minus 3 is 3, and 3 is indeed in our map, specifically at index 0. However, because we are also at index 0, this is not the answer, and we should continue looking. If we go to the next index, at index 1, we see if 6 minus 2, 4 exists in our map. We can do a quick constant time lookup to see if 4 is in our map, and we quickly find that we do. 4 is mapped to index 2, so we just return our answer 1, 2, and we're done. This algorithm has a runtime of O of n because we are, even though we scan through our array twice, it is a constant value and we're still linearly scanning through it a constant amount of time. Space-wise, it is O of n because we're using a map now to cache and store the values that we've seen in the index that they appear in, sacrificing some space for us to increase the runtime of our algorithm. There is actually one optimization that we can do to our 2-pass algorithm to make it slightly more efficient. It'll still be an O of n runtime, but it'll be twice as fast. And the idea is that we combine both of our scans into one operation. So first, instead of adding the value into our map, we'll actually just check to see if the target minus our current index value exists in our map. And if it does, then we have our answer and we're done. If not, then we add our current number and index into our map and then we continue. How that will look like is we start at index 0. We check in our map to see if we have 6 minus 3 equals 3, which in this instance, we still have nothing. So there's no existing pair. So we do our next step, which is add our current index into our map. So number 3 and index 0. And then we iterate to our next index. So now index 1, we check to see if 6 minus 3 or 3 is in our map. In this instance, it is. And because we have not added everything in our map before, that means guaranteed that the first number that we find, which means we have an existing solution and we can return that. Now in the live coding section, we're going to implement our 1-pass solution. First, we'll define our map. Like we mentioned earlier, we're going to scan through our array now. First, we'll check to see if the complement of our current value is inside our map. Otherwise, we'll just add it and its index inside our map for future iteration. Now, at the event that we reach the end of the for loop, which is not possible because this problem guarantees that we have an answer, we can maybe just throw an exception or just return anything because at this point, anything goes. So in this case, I'll just return a random array. To quickly run through our code, we start our for loop at I equals 0, which is right here. We first calculate our other variable, which is our target, 9, minus the value at index 0, which is 2. So is the value 7 inside our map? It's not. So we add 2 into our map. 2, 0. And then we move on to the next index. At index 1, we see if 9 minus 7, which is 2, is in our map. And if we look in our map, right over here, it does exist. So what we do is that we just return the index of our 2, which is 0, and the current index that we're at, which is 1, giving us the answer 0, 1. So now let's quickly run our code and see how we do. And there we go. This is how we would solve the two-sum problem. If you found this video helpful, please consider hitting the like button and maybe even subscribing for daily updates. Otherwise, I'll see you in the next video and have a great day.